So let's have a look. We have here the conjugated dienes. Now, the conjugated dienes are really a type of alkene. So really, it's like a super alkene chemistry. You should realize that we're looking at the classes and stability of these dienes. We're going to look at the synthesis. And of course, like alkenes, we will look at electrophilic addition to them. Remind yourself that addition is the removal of a degree of unsaturation. We'll be looking at thermal and the kinetics of this. We'll move deeper into the linear combination of atomic orbitals, and then further our knowledge on these conjugated dienes when we start to look at pericyclic reactions. Among the pericyclics, we'll be looking at cycloadditions and electrocyclic reactions. We won't be covering sigmatropics. And then I'll top it off with some UV-Vis. So let's have a look at what exactly we're talking about. In the past, you've looked at resonance. Resonance really is telling you that you have at least 3 p orbitals perpendicular to a plane of molecules, or a plane of carbon atoms even. So here, for example, these are the simplest species that you can have where we have a conjugated system, where we have resonance. We have an allylic system. Now, of course, the allylic system can be radical, it could be a cation, or an anion. I personally will be just briefly looking at heterolytic systems. Yeah, so we'll be looking at both the cationic species and the allylic species. You can see there's other examples of this conjugation. So classically, the one we focus on the most are these conjugate dienes. But of course, you can see here we have these 2 double bonds here in conjugation, and this is not a C double bond C. It is a C double bond O. Here we have an alkyne conjugated to an alkene, but it's the same principle. It's a principle of 3 p orbitals perpendicular to the plane of the molecule. So here are some categories of dienes that you should remember exist. We have the cumulative system. You can see that in center here we have an sp hybrid carbon. This is quite a high energy system. It's not very stable. Here we have a conjugated system, which is very stable. And here we have an isolated system. What we mean by isolated is that you can see that these 2 double bonds are isolated from each other. They're not conjugated. So on closer expansion, you can see that this sp3 hybridized carbon, yes, separates out these p orbitals that are perpendicular to the plane of the molecule here and of the molecules here. So if we look at the p orbitals themselves, you can see that this is the case of the isolated system, and here's the sp3 carbon. Yeah, so all the p orbitals are used up in the hybridization, and so never the twain shall meet. So these 2 double bonds, 1, 2, will not be conjugated. Here, however, you can see that all of these guys are adjacent to each other, perpendicular to the plane of the molecule, and therefore we have conjugation. We'll actually be looking quite a bit at these 1, 3, 5 systems in the near future. So let's move on. There is quite a wealth of conjugated organics. You can see that here, for example, we have the cyclopentadiene, and these 2 double bonds are conjugated, similar to the 1,3-pentadiene. On closer inspection, you can see that here in this benzene ring, we have all of these 3 double bonds conjugated. But look, it is isolated from this fella, from this double bond. Here we have a ring, 3 double bonds, and it's conjugated to this, and then of course it's conjugated to this ring as well. On the other hand, when you look over here, you can see that in this 1,2-diphenyl ethane, you can see that there's a benzene ring here, but it's isolated from this benzene ring. Doesn't have to be a carbon-carbon bond, because you can see with the azos why this double bond here is conjugated to this system and this system. So this whole system is conjugated. And we will have a closer inspection of species like this in the near future. We can ask a question like this. It asks you, which compound does not have a conjugated system? Immediately you realize that every single compound except for C, yeah, has the double bond conjugated. Here C is showing you an isolated system. Here's the sp3 carbon, and that double bond is therefore isolated away from that double bond. Certain features that are evident in these conjugated systems is the short distances of the C to C3 bond. It's a very short bond, yeah, compared to a normal carbon-carbon single bond. This is the bond length of 1,3-butadiene. On closer inspection, what we've noticed, yeah, so it's 1.47. Here, the alkene, of course, quite short, 1.34. In a regular alkene, yeah, the alkane, the carbon-carbon is at 1.54 Armstrongs. So you can see there's a difference of 0.07 Armstrongs. Yeah? The argument is that, of course, there's sp3 overlap, and of course, with the P contribution being so strong, then of course the overlap is not as great. On the other hand, you can see here, if we have in this 1, 2, 3, 4, this 1 butene, you can see that we have an sp2 overlapping with an sp3, so we expect overlap to be a bit better, hence the shorter bonds. And of course, yeah, you'd expect there to be an even greater shortening here when you have the alkyne. So with the sp3 overlap. So this phenomenon can easily be explained by the hybridization of the carbon. So we say sp2 overlap, yeah, is quite efficient, and hence you get a 1.47 Armstrong. Personally, I prefer the molecular orbital traces of this, and we will have a look at that later. It's much more elegant. So we move on. We also look at the relative stabilities, like all type of alkene chemistry. We have to look at the stabilities, and how we do that, we just hydrogenate. So in this case, hydrogenation, yeah, realizes the parent alkane. Yeah, so you remove all the double bonds or triple bonds that you have in your compound, yeah, to give you an alkane. You can see, quite simply put, if we look at a simple picture here, 2 of these 1-butenes, that means 2 double bonds in the same sort of environment as this 1,3-butadiene, yeah, 2 of them is equivalent, yeah, will give off 254 kilojoules of mole when I hydrogenate. However, when I hydrogenate the conjugated system, I only generate 239 kilojoules per mole of energy. That's a difference of 15 kilojoules per mole. This is called, yeah, the resonance stabilization energy, yeah, or the energy saved due to conjugation. We can see quite a few examples of different unsaturated species, and you can see that the conjugated system has generates the least amount of energy when we hydrogenate, meaning that it is the lowest energy system, the most stable system. And so we can ask something like this. Immediately here, what you would want to do is you want to draw the compound in each case, and then you try to analyze these figures and see which one is the one that will give you the smallest heat of hydrogenation. And here I will pause for a sec for you to work this out. Immediately you can see that this is the conjugated system. This is an isolated system. This is a simple alkyne, and this one, of course, is a cumulative system. So one question I could ask quite easily is, give us the order of stability. Now that would be an interesting question to put on the exam. Synthesizing these conjugated dienes is quite simple. Yeah, you can see that we can have this allylic bromine compound. So you can have an allylic system and brominated with, say, for example, NBS, and then we use the tert oxide to eliminate, yes, and that will generate our conjugated system. You can see that we also can use a dibromo species like this, and we use the tert oxide, and of course it will eliminate across here and here, yes, to give us our conjugated system. You can envisage, right, you have a double bond in here, and then you treat it with dibromine to give you this dibromo species. The question I should ask you is, what would happen if we have a less steric base, such as this ethoxide? Here is a typical example of the synthesis. You can see that we have the alkene. We treat it with the N-bromosuccinimide. Remember that this occurs via radical mechanism. And then, of course, you got the bromination. Elimination with the butoxide realizes your conjugated system. And so we go to the main thrust of this section, and that is the electrophilic addition to dienes. Namely, electrophilic addition to conjugated dienes. I just want to briefly look at the allylic cation, and then there is a section on the resonance. I'll give you that in a handout, so I'll expect you to review that. In the meantime, I'm going to go through, continue to talk about the mechanism of this addition and the two possible products, i.e. that which is of kinetic control and that which is of the thermodynamic control. So I personally recommend you to go through the slides, upcoming slides on resonance, and then you can get back to this part of the lecture. Remind yourself that resonance is, of course, there is no change in the skeleton structure, just movement of lone pairs and pi electrons. So in this case here, we have a cation. We move that lone pair into that space because these three carbons here are the ones that are in resonance, because those are the ones with the p orbital perpendicular to the plane. On the other hand, you can see that here we have a species, right? And we have this looks like a hydride shift. This is not a resonance structure of the other, because you move some sigma bonds. You can see here, for example, another case where we have something weird, because you push the electrons into there, but now you have a 10 electron carbon, pentagonal carbon, and that's not good either, is it? So work on those, and we can continue this part of the lecture. So I'll pause here. We need to also observe carbocation stability. We've learned this from some time ago, whereas you can see that the tertiary carbocation is quite stable compared to, say, the secondary and the primary the stability, of course, via hyperconjugation. Here you have an allylic cation, and of course it's stabilized by resonance, and this is very good. But of course this is an allylic cation which has a primary carbon cation in this position. On the other hand, you can see that here we have the most stable beast of all, because we have an allylic species, but not only that, the carbon associated with this allylic species, this carbon cation, is tertiary. So it's a combination of an allylic system and hyperconjugation, or robust hyperconjugation. So this is a very stable species. We could easily ask something like this: which alkene is least reactive in an acid catalyzed hydration? In a case like this, what you really want to know is which compound produces the least stable carbon cation. Have a think about that, and we can come and talk about it the next time we meet during our discussion. So I'll pause right here. So here, and we're talking about the electrophilic attack on conjugated dienes to produce the 1,2 and 1,4 addition. We find that at very low temperatures, when we have a conjugated diene with an electrophile, we have the 1,2 product, the 1,2 adduct dominating, assuming that this is carbon 1, this is carbon 2, carbon 3, carbon 4. 1, 2, 3, 4. At high temperatures, then we have the 1,4 adduct dominating. This is thermodynamic control. Remind yourself of this when you do attack a alkene to generate a carbon cation. You really want the Markovnikov carbon cation. This is no different, but here we have a conjugated system. Why? So what we're going to try to do is try to open up the conjugated system so that we have the most stable carbon cation. That carbon cation, of course, has to be allylic. Have a think. So this allylic system will generate your kinetically produced products. So you can see that here at low temperatures, this is the kinetic species, and of course at high temperatures we end up with your kinetic species being very low and the thermodynamic species very high. Look at the difference, because the kinetic species is the least substituted alkene. There's only one R group on the alkene at present. On the other hand, you can see that the thermodynamic species is disubstituted in this case. The mechanism looks like this. Opening up with the HBr is typical. Yeah, you have the HBr, you have nucleophilic attack on the electrophilic hydrogen bromide. This, of course, hydrogen is the electrophilic center. And you end up with a carbon cation. There should be a plus here, by the way. I should really fix that. So this is a carbon cation right here. And here we have a carbon cation as well. You can see that this fella is a resonance structure of that guy. So extraordinarily, we have the bromine attacking both species, and of course, if we, in this case here, yeah, we end up with the 1,2, and in the second case we end up with the 1,4. The 1,2, of course, is the kinetic species, and the 1,4 is our thermodynamic species. This is quite a simple question, because I'm asking you which compound could react with the DCl to produce this compound shown. We have 4 options. Now, what I would like you to do is have a little think. Yeah, I'll pause it right here. You should pause as well. Have a little think and think about, yeah, which product is, which compound was the likely starting material. Did you pause? I hope you did. If we look at the energies involved in this mechanism, yeah, you can see that the 2 products, yeah, the 1,2 and the 1,4, yeah, have different energies, because the 1,4 is of course a disubstituted alkene, so it would be of lower energy than the 1,2. On the other hand, because we're going via a more stable carbocation, then of course this transition state dominates over this one, and so it is of lower energy, i.e. the activation energy in this case is much lower. So at low temperatures, that's why this dominates. Low temperature, follow the graph here. Yeah, a low temperature. Sorry about that. Let's get rid of that. At low temperatures, you can see that, yeah, we end up with this dominating. And of course, at high temperature, yeah, we have this dominating. Here's a question you can ask yourself, and you can see, of course, it's obvious that the 1,2 is the kinetic and the 1,4 is the thermodynamic. We don't have to use some hydrogen halide. You can see that here, for example, we have a dibromine. And dibromine can give you the 1,2 adduct or the 1,4, depending, of course, on the conditions. We also have this interesting species because this is isoprene. Yeah? And of course, isoprene is the monomer for rubber. Yeah? Now you think about it for a second. This polymer is a product of 1,4 addition. 1,4 addition is, of course, yeah, thermal. It's like high energy. You need a lot of heat, yes? High temperature. Yeah? Why don't you give us a mechanism for this? We can maybe work on it next time we meet. And so I want to talk about the linear combination of atomic orbitals. It's okay because all I'm going to do is review molecular orbital theory, and then of course we can see how this theory strongly supports the bond lengths observed in the conjugated butadiene. We'll also briefly look at frontier molecular orbitals, and then we'll look at thermal systems versus photochemical systems. So here is a brief look at molecular orbitals. So for example, the simplest you can think about as far as the pi system is concerned, pi bond is concerned, is of course you have 2p orbitals overlapping in a plane. You can either have them overlapping, yeah, where the bonding is of course the same flavor, i.e. the phases are reacting. You can see blue with blue, red with red. Yes, and then of course you can see that we can have them where the flavors oppose each other, or the colors oppose each other, or the signs oppose each other. This is of course constructive bonding, and that would give you bonding orbital a bonding orbital, complete overlap. This, of course, is destructive bonding, and that will generate a molecular orbital of higher energy called the anti-bonding molecular orbital. Two p orbitals combined at this energy level, yes, and we generated two molecular orbitals of equal but opposite energy. So this one is a molecular orbital that's stabilized, and this one is destabilized. When you add them together, you still get the energy of the two orbitals that you start with in the first place. So two atomic orbitals combine to give you two molecular orbitals, psi1 and psi2. And here we have a little star, so this is psi2 star, to indicate that this molecular orbital is anti-bonding. Realize that in a pi bond, each p orbital will have one electron, and so in this molecular orbital picture, we have two electrons. And of course, once you fit them in according to Aufbau and Hund's rule, then of course you can see that we have one pair of electrons here and 0 here. The bond order, remind ourselves, the bond order of this species equals to the bonding pairs minus the anti-bonding, I'm just going to shorten this if you don't mind, anti-bonding pairs divided by 2. So in this case here we have two bonding, that's these two here, that's this two here, minus 0 anti-bonding here, divided by 2 equals to 1. So the bond order is 1. And of course it is, because the bond order of one pi bond is of course 1. There's only one pi bond. Here in the allylic system, it's very interesting because, yeah, why not? Yes, the allylic system, you can see that we have 3 p orbitals, and you have a bonding psi1, a non-bonding psi2, and an anti-bonding psi3 star. So if you look, say for example, at the allylic anion, you can see the bond order is 2 minus 0 divided by 2 equals to 1. Remember that this P is represented here. It's non-bonding. Here is our butadiene. It's very pretty. You can see that we have 4 p orbitals combined together. 4 p orbitals combined together to give you 4 molecular orbitals. Psi1, Psi2, Psi3, and Psi4. Psi1 and Psi2 are bonding molecular orbitals, and Psi2 and Psi4, Psi3 star and Psi4 star are anti-bonding molecular orbitals. Look at it carefully, because there's a couple of things that I needed to make notes of. If you note, in Psi1, at no time does the flavors change. Yeah, above, below the plane, right? So there's 0 nodes. Here, you can see there's a change in flavor right here. Yeah, it's a wave function, remember that. So the change in flavor, there's 1 node. Yeah, flavor here it's green or whatever, and here it's green. So there's change in flavor right there, 1 node. And of course, 2 nodes. So Psi1, 0 nodes, Psi2, 1 node, Psi3, 2 nodes, etc. the more nodes you have, the higher the energy. So increasing the nodes increases your energy. Remember that. Bond order, of course, is 4 minus 0, 4 bonding, minus 0 anti-bonding, divided by 2 equals to 2, i.e. it is the conjugated diene, and there's 2 pi bonds. Remind yourself that these molecular orbitals only represent the pi bonding in this molecule. 4 p orbitals combined together to give you 4 molecular orbitals. The interesting thing about the work that we'll be doing throughout this chapter is this idea of the frontier molecular orbitals. Look at it carefully, because in all of the pericyclic reactions that we'll be working with, these are the only molecular orbitals that's going to be important to us. The highest occupied molecular orbital and the lowest unoccupied molecular orbital. The highest occupied molecular orbital, obviously, is in this case occupied by this pair of electrons. The lowest unoccupied molecular orbitals, unoccupied of course meaning that it is got no electrons. This is your band gap. That energy gap there, we'll look at it in UV later on. That energy gap, yeah, falls in the UV visible. And so we'll probe this later when we look at UV-Vis spectroscopy. Another feature I want to point out to you is this. If you look carefully at these, the Psi1, look, here we have a blue, here we have this p orbital here, that end it's blue, here we have it's red, and over here it's red. So on both ends, we have the same flavor, the same color. We say that this molecular orbital is symmetrical. On the other hand, if you look at Psi2, you can see that here we have red, and over here we have blue. Here we have a red. You can see this one, of course, is blue at that end. So this molecular orbital is asymmetrical. Terribly important. Yeah, you can see that we went from symmetrical to asymmetrical to symmetrical to asymmetrical. Yeah. Later on, we'll be talking about the importance of these ideas. Frontier molecular orbitals. If we hit the molecule with a photon of light equivalent to this energy, then of course we will excite that molecule. We will excite a pair of electrons. This pair of electrons will excite an electron from this molecular orbital up to here. And this is what we have right now. So what happens then? When we hit this with light, we end up with this situation where Psi3 is now the highest occupied molecular orbital, and Psi4 is the lowest unoccupied molecular orbital. So we can ask a simple question like this: what type of system is this representing? And of course you can see we have a singlet occupied Psi3, and so that has to be photochemical because it's an excited system. Here, molecular orbitals theory has an elegant way to explain the bond length of the C2C3 in the conjugated butadiene. 1, 2, 3, 4. So we're talking about the C2C3 bonds. Yeah, it's quite simple, because if you look at Cy1, yeah, here, yeah, there's a pair of electrons that reside in it, meaning that there is pi bonding between C2 and C3. Is it? There is overlap between those, yeah. So there is, because there's overlap, then of course there is pi bonding between C2 and C3. It's not shown in the Lewis structure, is it? That's shown as a single bond. But from the molecular orbital treatise, you can see there's pi bond, and if there's pi bond, then of course the bond is shorter. Here we're looking at the conjugated triene, in this case a 1,3,5 triene, and of course we can see that in this case, if we, yeah, Cy3 is the HOMO, and the ground state is in the ground state, the LUMO is Cy4 star. But if we excite the molecule, yeah, with light, then of course the excited state is now the excited HOMO is now Cy4 star, and the LUMO is Cy5 star. So that's a change in your frontier molecular orbitals on excitation. So I'd expect to take a break now, and we'll continue with this lecture in a few moments. So here we'll have the coverage of pericyclics. There are some parts in chapter 16, and there's a small amount of electrocyclics that is present in chapter 30. We'll be mainly concerned with cycloadditions and electrocyclics and molecular orbital treatise of both situations. You should see that pericyclics, unlike what we've done in the past, in the sense that we've done homolytic, which is radical systems, or heterolytic systems, you know, where you have some sort of charge transfer. In this case here, we have a cyclic transition state. So it's a concerted reaction, and of course, it can be either thermal or excited. And as we know, when we go through a transition state, what we're trying to do is we're trying to avoid intermediate. So intermediate is skipped, and we have a transition. This is a one-step concerted reaction. The three categories that we should focus on are those of cycloaddition, electrocyclics, and sigmatropic rearrangements. Cycloadditions, as you can see, yeah, we started off with three, in this case, we start off with 3 degrees of unsaturation, 2 here and 1 there, and we end up with 2 degrees of unsaturation, 1 degree in the ring and 1 as a double bond. And so we've lost a degree of unsaturation, hence it is an addition reaction. So what? The product has 2 fewer pi bonds than the reactant. In electrocyclics, you can see that we have, in this case, a ring opening. We started off with 3 degrees of unsaturation. Now we have a species with 2 double bonds and a ring, and so literally we still do have 3 degrees of unsaturation. However, we've lost 1 degree of unsaturation to a sigma bond. So we now have a new sigma bond. The reverse of this will be the ring opening, where we gain this pi and lost a sigma. So we lost the pi, gained the sigma, and the reverse is losing a sigma and gaining a pi. Sigmatropic rearrangement, exactly what it is, right? You can see that we've rearranged the species. So I can answer questions like this: which of the following is classified as an electrocyclic? And remember now that in electrocyclic, whether it's a ring opening or ring closing, there shouldn't be any change in the degree of unsaturation. So what I'm going to ask you to do is pause, and then we'll look at this during class. Here we have a situation where we're asking which one is sigmatropic. Sigmatropic is kind of easy to recognize, because then in this case here, all it is a rearrangement. That's the rearrangement. So the first case that we'll be focused on is the cycloaddition, the most important case. Yeah, it's covered quite extensively in the literature. And remind yourself that cycloaddition is that each reactant will lose a pi bond, and the resulting cyclic compound has two new sigma bonds. The two situations we're looking at is, of course, the Diazolda, which is a 4 pi 2 pi, meaning you got 4 pi electrons and 2 pi electrons involved. And of course we have a photochemical situation where we have the 2 pi 2 pi. So the Diazolda is thermal, and this fella here is of course the photochemical, the 2 pi 2 pi. Let's have a closer look. In the Diazolda, we say we have a thermal 4 pi 2 pi because it is a ground state molecule, or ground state molecules that will be reacting. We're going to cover the thermodynamics, some kinetics, and we're going to look at some stereospecificity and the molecular orbital treaties. What we've noticed is this: we have a diene, which has 4 pi electrons, of course, it's a conjugated diene, will react with a dienophile, a diene lover. And so that's got 2 pi electrons. And the result of this Diazolda is a cyclohexene ring. A cyclohexene ring. We started off with 3 degrees of unsaturation, and now we have 2 degrees of unsaturation, hence an addition. Woodward and Hoffman are the first guys that came up with this lot, or the guys that sort of like reported it in the early stages. And you can see the 4 pi 2 pi to give it the cyclohexene. The mechanism is kind of easy. You show a concerted movement of electrons. So here we have the 2 new pi bonds being 2 new sigma bonds being formed, and here we have some pi bonds being broken. So here are the new sigma bonds, and here is a new pi bond. Of course, it is a cycloaddition. Have a look at that, answer the question, and we'll probe it when we come back. So I would expect you to pause here as well and try to elucidate an answer. This is the energy diagram involved in the Diazolda. So the diene and the dienophile are reacting, and if you look, we're looking at free energy here, and you can see that the reaction, being spontaneous, is exergenic, passing through the cyclic transition state. Now, what I want you to remind yourself is that it is exergenic because, the enthalpic content of this reaction is quite high, because we went from high energy pi system to low energy sigma. So here you can see that we got 3 pi bonds being broken, and what we end up with is lower energy sigmas and only 1 new pi bond. So of course it is pumping out a lot of energy, i.e. it is exothermic. So this term here is quite high because it's exothermic. However, what we found is that if we heat this thing greater than 200 degrees Celsius, this cyclohexene ring, we have what's called a retrodiazolda that takes place. And for us to understand exactly what's going on, we have to probe this free energy equation a bit deeper. You should realize that this minus T delta S term is positive. So if you note, the delta S is positive, is negative, because you can see there is a reduction in entropy. Yeah, 2 molecules going into 1. So that's why this is positive. If we increase this temperature, then of course this entropic term will now overwhelm this enthalpic term, and this will now be positive. If this is positive, then that means it's non-spontaneous. Non-spontaneity means that we have the reverse reaction. Remember, the forward reaction is spontaneity, yeah, all right, and non-spontaneity is, of course, the reverse. In the kinetics, we really need to probe the stereochemical requirements of the Diels-Alder, because here we need an S-cis conformation compared to an S-trans. All it is that in the S-cis we have a sigma bond with both double bonds on the same side in the conformal. Yeah, in this case, in the S-trans, we have the double bonds on opposite side of that sigma bond here. For the Diels-Alder to occur, we have to have an S-trans conformation. So here, for example, you can see we have a conjugated diene, and this reaction will not work because we're trapped in an S-trans. This conjugated diene is trapped in an S-trans. On the other hand, cyclopentadiene is so reactive that one molecule will act as a dienophile, and then the other molecule will act as a diene, and so the Diels-Alder will happen. Yeah, so the species dimerize. We could ask a simple question like this, and further analysis of it, you can see that, yeah, that this number 1 is trapped in the S-trans. Can you see that? Every other molecule, yeah, is trapped in the, is either trapped in the S-cis. This one is trapped in the S-cis. So this is really the fastest. And then, of course, we can rotate around here to give us the S-cis, rotate around here to give us the S-cis conformal. Substitution on the dienophile is terribly important. You can see that we need an electron withdrawing group on this. And so here, for example, we can see we have, yeah, sort of a conjugated species, which is, in this case, is a enone. All of these are enones except for this nitrile species. Well, you can see that here we have an electron withdrawing group, yeah, on the dienophile. And so that will increase the speed of the reaction. In fact, you get full conversion here. You can see in this case here we have electron withdrawing groups, yeah, here and here. But here we have an electron donating group. And so this reaction is very slow. On the other hand, we have 2 electron withdrawing groups, and so this reaction is very fast. One thing we note is this stereospecificity of the Diels-Alder is terribly important. Yeah, if we have, for example, a dienophile where the withdrawing groups are Z's, yeah, you can see both groups are on the same side of the double bond, then we end up with a cyclohexene ring where the groups are cis on the same side of the ring. In the case of this fella here, you can see both withdrawing groups are, E, i.e. trans, and so we end up with a ring where the two groups are anti or trans to each other on the ring. Try to look at this situation and explain it for me. In this case here, the substitution on the diene is what determines these groups on the ring. So we could easily answer a question like this, and of course you can see that the electron withdrawing groups on the dienophile are Z's, and so on the ring you'd expect them to be cis. So that removes this option, because you can see that here those electron withdrawing groups are trans. You should also see that here around this species we have an E, and this double bond is a Z. You can see E, well, that's trans, and that's cis Z right here, this double bond. So if you got an EZ, then of course on the diene, then of course we're going to end up with these methyl groups here and here being trans on the ring. So here we can see there are cis on the ring, so that option is out. See, cis, methyl cis on that ring, so that option is out, and so we're left with option B. That is incorrect. We're left with option B. And lastly, we talk about the Ender rule. And the Ender rule is quite an important rule for us. All we got to remember is this, that if we have a ring system, if our diene is in a ring, then we're going to have some sort of bridgehead carbon. If it's a 5-membered ring, we have one bridgehead. If it's a 6-membered ring, we're going to have a double bridgehead. Traditionally, we use this bold line to explain to the reader that the bridgehead is pointing towards us. And so if we had any groups that are on the opposite side of the 6-membered ring, it would be hatch. You can see here, this is how we represent it in a 3D structure. Realize that here's our 6-membered ring. And this is the bridgehead. Any species that is opposite that bridgehead here is endo, and if it's on the same side as the ring, the 6-membered ring, then it's exo. So this group is exo, and this is endo because it's opposite the bridgehead. When we have electron withdrawing groups on the dienophile, the major product is endo. And for a simple reason, the electron withdrawing group has some sort of delta plus associated with it, some sort of partial positive charge, and that will interact with the electron-rich diene. That interaction, once the click happens, i.e. once the two sigma bonds are formed here and here, then of course the electron withdrawing groups are in an endo position, not exo. So here's a simple one. You can see immediately, that the click will not have an impact on the methoxy groups, but of course this is what we're looking at right now, that group, and of course you can see that it should be, yeah, it will be endo to the bridgehead. This is a very nice question. I expect you to work on that, and then we will review that in class. This is a very nice way to reverse the disorder so we can see the starting diene and diener file. What we got to do is identify, first of all, the 6-membered ring. So we've done it here. That's the 6-membered ring, you can see, yeah. And then, of course, we draw some arrows that show bond making and bond breaking to generate our diene and our diener file. Here you can see these two groups here were sister ring, and so in our diener file, yeah, then of course they are also in that position. So this is, of course, a Z. In this case here, identify the ring. You can see the ring right here. Yeah. So if you identify the ring, then you can start moving some electrons around. And then, of course, you end up with your starting diene. And, of course, your diener file. Why don't you try to do this one for me? And then we'll talk about it in class discussions. So that's the end of that period. What we're going to try to do next is take a pause, and then we start the next section. The next section, of course, will be uploaded as a different slide from this one, and we'll find these similar to how you found this one on a link, a YouTube link.